In the last video, I said I'm getting a little bit ahead of myself, but I'm saying it anyway. If you have dipoles along bonds that cancel out, we're going to call that thing nonpolar. If you have dipoles that don't cancel out, we're going to call that thing polar. Yep, hold on. So who's more electronegative, nitrogen or hydrogen? Nitrogen. And because nitrogen is more electronegative, we have a dipole along all of those nitrogen-hydrogen bonds. Dipoles pointed toward the nitrogen. So if we sum together these three dipoles, part of the dipoles would cancel out and part would not. We would have a net dipole that's pointed upwards in this ammonia molecule. When you have a net dipole, we're going to call that molecule polar. So in order to talk about something being polar or not polar, number one, you need to be able to draw the Lewis structure. Number two, you need to know the shape of that Lewis structure. Number three, you need to detect bond dipoles. And number four, you need to know if those bond dipoles cancel out or not. So if I know the shape of this is trigonal pyramidal, it's not three H's all in the same plane, because if they were three H's all in the same plane, they would cancel out. Trigonal pyramidal, no way. Those arrows do not cancel out because of the bond angle that they're aiming toward. Okay, so if we're talking about methane over here, CH4, does it have a bond dipole? Yes. I'll talk to you about that. CH4 has a bond angle pointed toward carbon. Hydrogen is slightly less electronegative than carbon. So there's a bond dipole among all of these pointed toward the carbon. Do all four of those vectors cancel out? When you add those four vectors together, they all cancel. And because they all cancel, we would call this molecule nonpolar. Yep, we would. So why does polar and nonpolar matter? Delta H of vaporization of 23, delta H of vaporization of 8.3. What is delta H of vaporization? Well, it tells you the physical properties of polar and nonpolar molecules are different. And so something that is polar has higher delta H of vaporization. It means it's harder to get into the gas phase. It takes more energy to get this polar molecule into the gas phase than it does this nonpolar molecule. The boiling point of this nonpolar molecule that has similar molar mass, the boiling point of this nonpolar molecule is going to be smaller than the boiling point of this polar molecule. The physical properties of polar compounds are different. Okay. Which of the following have a dipole moment? AKA, which of the following are polar? In order to know if it's polar, you have to be able to draw the Lewis structure, know the shape of the molecule, know the electronegativity differences to know if there are bond dipoles, and be able to add those bond dipoles together and know if they cancel out. So, H2O, that's water. Here's his Lewis structure. Who's more electronegative, hydrogen or oxygen? Hopefully you say oxygen. Dipoles pointed toward the oxygen. Do those dipoles cancel? No, because water is bent. If water were linear, they would cancel. But water is bent. It does not cancel. There's my net dipole. I'm going to say this thing is a polar molecule. CO2. Do you know the Lewis structure of CO2? That's it. Who's more electronegative, carbon or oxygen? Oxygen. So we have a dipole along each of those bonds pointed toward the oxygen. Do they cancel? Yes. Because they cancel, it's a nonpolar molecule. The boiling point, melting point of something like water versus something like CO2, very different. Polar and nonpolar compounds have different physical properties. SO2, what does its Lewis structure look like? You should practice drawing Lewis structures. It's been a minute. There's the Lewis structure of SO2. O is more electronegative than S, so you have dipoles this direction. It's bent, just like water is bent, which gives me a net dipole absolutely. It's polar. CH4, we've already seen it. There are dipoles pointed toward the carbon. They all cancel. Nonpolar. Yeah. There are 3 different structures of this thing. Are they all polar? No. These 3 different structures, they're called isomers, things that have the same molecular formula but different connectivity. So I've got carbon to fluorine. So carbon to hydrogen is a very similar electronegativity. So we often talk about carbon-hydrogen bonds being nonpolar. We don't talk about them having a dipole at all. So our carbon-fluorine is really what we're most concerned about in each of these cases. So carbon to fluorine, we've definitely got a dipole pointed toward fluorine, a little one coming from the hydrogen too. Toward the fluorine, toward the fluorine. So this toward the fluorine, definitely going to have a net dipole. It's polar. These are equal and opposite, completely balanced, nonpolar. These are pulling the same direction, net dipole for sure, polar. While I'm here, and because I'm an organic chemist at heart, we would call this molecule cis. We would call this molecule trans. We would call this molecule neither. Yeah. If you've ever heard the word cis and trans as it applies to molecules, that's what that means. So I said hydrogen and carbon have very similar electronegativity, very similar. So we usually don't talk about hydrogens and carbons having polar bonds. So anytime you have something that's a simple hydrocarbon, meaning only hydrogen and carbon in the whole molecule, rather than saying there's a bond dipole here, bond dipole here, bond dipole, bond dipole, bond dipole, bond dipole, instead of saying there's all these CH bond dipoles, we're just going to say it's not very significant. This molecule we would call nonpolar. But anytime you throw in something like a heteroatom, is what an organic chemist would call it, an oxygen, a nitrogen, an oxygen, we would call this molecule polar without even thinking about adding up all of the bond dipoles because it's not symmetric. So these two might cancel each other out because those two are kind of equal and opposite pulling away. But these are not symmetric, so they're going to be pulling, period, and they're going to be pulling differently, so they cause this molecule to be polar. BCl3, we got to know how to draw the Lewis structure. We got to know what kind of shape it is. It's trigonal planar. So yes, there are dipoles along these bonds pointed toward the chlorine in each case, but they would all completely cancel. BCl3 is nonpolar. What about PCl3? PCl3, I have practiced my Lewis structures more than I bet you have practiced your Lewis structures. Phosphorus has a lone pair in PCl3. So definitely, this is trigonal pyramidal Ig, causing those dipoles toward chlorine to make this molecule polar. BCl3, nonpolar. PCl3, polar. That lone pair on the phosphorus makes all the difference. Hydrogens and carbons, we don't care about that so much, but not symmetric stuff that's not hydrogen-carbon, polar. Yeah. Practice your polar, nonpolar assignments. Goodbye.